Welcome to this HP Expert 1 presentation. In this video we're going to look at the OSI model with an emphasis on how devices communicate. The Open Systems Interconnection Model, or OSI model, is a critical building block for your understanding of networking. You will often hear network engineers discuss issues by saying that the problem is at layer 1, or we have a network fault at layer 3, or this is a layer 4 issue, or even we may have a layer 7 issue. To understand what that means, you need to have a good understanding of the OSI model. The OSI model is important for troubleshooting and understanding networks and network protocols. In this video, we're firstly going to look at why do we use the OSI model. What advantages are there to using this model in networking today? Then we're going to look at the layers of the OSI model, and that is where those terms, layer 4 or layer 7, come into play. I'm going to show you how traffic flows between hosts with specific reference to the OSI model. And lastly, I'm going to show you how the OSI model is used in the real world by sniffing traffic using a free application called Wireshark. Wireshark is a sniffing application that allows us to see traffic on the network. In this example, I'm going to open up a web browser to a server on the internet, and we'll capture the traffic and see what it looks like. Because of the length of this video, it's been broken up into two parts. In the first part, we're going to look at why the OSI model and the layers of the OSI model. In the second part, or second video, we're going to look at how traffic flows between hosts and sniff the network using Wireshark. If you're comfortable with the layers of the OSI model and just want to see a practical demonstration, please jump to part 2. Otherwise, continue watching for the reasons for having the OSI model and the layers of the OSI model. The OSI model is often used to explain communication between devices in a network. It makes it easier for network engineers to discuss specific issues with devices such as hubs, routers, or switches. When host A sends traffic to host B, how does that communication actually take place? And at which layers of the OSI model do devices such as switches or routers operate? There are multiple advantages to the OSI model, and let's look at a few of those, and then I'll explain each of the layers in a lot of detail. Now, in the past, there were older models that were proprietary and were typically controlled by a single vendor. This caused multiple issues, especially in networking, where we have many different devices that need to communicate. Issues resulting from a proprietary model included slow development and poor or no interoperability. For many years, there's been a huge drive to standardize protocols, and HP is committed to interoperability and open standards. The OSI model was developed by the International Organization for Standardization, or the ISO, and provides a layered approach to development and interoperability. It allows for multi-vendor interoperability and rapid development. Thus, for example, Internet Explorer, developed by Microsoft, can connect across an HP network to a web server running Apache on top of Linux. That kind of interoperability and communication is made a lot simpler because of the OSI model. We have seamless interoperability where traffic is sent between multiple vendors and applications. Now, the OSI model consists of 7 layers, with the advantage that each layer is independent of other layers. The layers of the OSI model, starting from the top, or layer 7, are application, presentation, session, transport, network, data link, and physical. Physical being layer 1. When discussing the OSI model, we typically explain and reference it from the bottom up. So layer 1, layer 2, 3, 4, 5, 6, and 7. There are many different ways to remember the different layers. One of them is all people sleeping through networking don't pass. But I'm sure you'll encounter many sayings to help you remember the layers. Now, I'll be going through each of these layers in a lot of detail in the following slides. Please bear with me, as this can get a little bit tedious, but it's really important that you understand the layers. It's going to help you immensely as an engineer to have a deep understanding of the OSI model, specifically when doing troubleshooting. There are multiple advantages, including standards and interoperability as mentioned. HP are committed to open standards. Another advantage is split development. An application developer, as an example, writing an application like Microsoft Word doesn't need to understand the details of IP routing and networking, which are at the lower layers of the OSI model. An application developer will be concentrating on layer 7. He doesn't need to understand the details of copper and fiber cabling. The layers are separated, so we have split development, which makes things less complex. When saving a file in Microsoft Word to the local hard drive or to a remote network share, the developer doesn't need to understand the finer details of iSCSI or SANS. He doesn't need to be concerned about whether the hard drive is local on the local machine or remote using a network share. From the point of view of the developer, he's only talking to the layers below him. So the operating system, for example, and other layers will take care of saving the application locally or on a remote network share. Now, as mentioned, from a troubleshooting point of view, it's going to make your life a lot easier understanding the OSI model. We'll be able to determine if it's a layer 1 issue, or a layer 3 issue, or a layer 7 issue. And once I go through each of the layers, you'll hopefully have a good understanding of why this helps you with troubleshooting. It's also great, once again, for interoperability. It allows for quicker development. In the last few years, there's been a great acceleration in the development of applications and technologies. Think of the fact that 5 or 10 years ago, sites like Twitter, Facebook, LinkedIn, and so forth didn't exist. Today, developers of, for instance, Facebook do not need to understand what an ISP is doing in the UK. They are just going to develop their website, and the ISPs will route traffic to those websites using different protocols like BGP or OSPF. So it's not necessary for an application developer to understand the details of networking. By the same token, a network engineer troubleshooting a network doesn't need to understand how Facebook works. In other words, doesn't need to understand the details of PHP or Apache servers. They can concentrate on network protocols, not programming languages. And lastly, it simplifies teaching and learning. Please ensure that you understand the OSI model because it'll give you a much better understanding of networking. We as network engineers will use names and numbers interchangeably, so we'll often talk about layer 2 or data link, or layer 3 or network. So just remember that layer 7 is application, layer 6 is presentation, 5 is session, 4 is transport, 3 is network, 2 is data link, and 1 is physical. Remember both the number and the name. Now, in the past, there used to be a major split of concentration in the OSI model. The top 3 layers were the focus of developers and server administrators. The lower 4 layers were the domain of the network engineer. These days, because of the growth of technology such as VMware and converged infrastructure, these roles are blurring. Often network engineers need to troubleshoot servers, and server admins may need to troubleshoot virtual switches within a VMware server. But traditionally, developers focused on the development of applications such as Internet Explorer, Firefox, and so forth, which reside at the application layer. They would need to understand, for instance, how to present data in specific formats, how operating systems manage sessions and interact with their applications, and they tend to concentrate their effort on the top 3 layers. Network engineers concentrate, in most cases, on the lower 4 layers of the OSI model, and this is the focus of this course. We're going to concentrate mainly on transport, network, data link, and physical. In other words, layer 1, layer 2, layer 3, and layer 4. It's a well-known joke in networking circles that developers will blame the network when their applications are running slow. In many cases, developers don't understand networking, and that's a byproduct of the OSI model. They don't need to understand networking because of the split roles and the split layers. They may be blaming the network for the performance of the application when in actual fact the reason could be something else, such as a server that's overloaded. But in brief, network engineers concentrate on the lower layers, server admins concentrate on the upper layers, even though those lines are blurring today. So I'm going to start off with a brief overview of layer 7, layer 6, and layer 5. And then we'll look at the transport, network, data link, and physical layers in more detail. So starting at the top of the OSI model, layer 7, or the application layer, let's work down through the various layers towards layer 1, the physical layer. Layer 7 once again is the application layer, and this layer provides network processes to applications. It acts as the window for users and application processes to access network services. This is a layer that a lot of people will be familiar with. The applications such as FTP, Telnet, and HTTP. Just note please that when we talk about the application layer, we are not talking about individual applications such as Firefox, Internet Explorer, or Chrome. We are discussing the application protocol, in other words HTTP, which those web browsers use. Or Telnet, we are discussing the protocol Telnet rather than an application such as PuTTY or TerraTerm. The same applies to other applications. Applications such as Firefox, Chrome, and Internet Explorer can function correctly because the applications are written to work with the protocol HTTP. And thus we refer to the application being HTTP rather than Internet Explorer. This layer provides those network services to the application, such as Internet Explorer, or whichever web browser you're using. This layer can identify communication partners, determine resource availability, and provide user authentication. Another example would be Microsoft Outlook. Microsoft Outlook is an application that works with protocols such as IMAP, POP3, and SMTP. Don't worry about the details of the individual protocols such as SMTP or HTTP or FTP. What you need to take note of here is that there are various applications that use protocols for communication with lower layers in the OSI model. A few other examples would be remote file access, remote printer access, resource sharing, directory services, and many other applications. So once again, the application layer is the window for users and application processes to access network resources and services. Layer 6, or the presentation layer, is concerned with the actual format that data is presented in. In other words, we're looking at data representation or syntax. The presentation layer ensures that data sent by one application can successfully be read by another application. So we need to ensure that the receiving system can understand the data, in other words, that it's readable. It's important to understand that different systems have different ways of formatting their data. So to ensure that the receiving system can receive and understand the data that it's receiving, the data needs to be changed to machine-independent format. There are some well-known examples here, including JPEGs, MPEG, ASCII, and so forth and so on. If you've ever tried to open a JPEG file in Notepad, you'll see what happens when the format is not understood. You just get a screen full of unrecognizable characters which aren't of any use. So this layer formats data to be presented to the application layer. It structures the data. It negotiates data transfer syntax. An example would be using ASCII or Unicode for the transmission of data between two systems. It can also provide encryption. So when you're sending, for instance, a music file from a Linux-based machine or Linux-based machine to a Windows machine, this layer ensures that the data is transmitted in a format that both sides understand. So as an example, using an MP3. You, for example, can connect to a website using Apache as the web service running on a Linux server from your Windows machine and view pictures and listen to music, watch videos and so forth, because the data is presented in a format that both sides understand. The session layer is concerned with inter-host communication. So this layer is involved in the establishment, maintenance, and termination of sessions between applications. This allows for two application processes on different machines to establish a session between them. This acts as a coordinator of communication between systems. Examples of protocols that exist at this layer include remote procedure calls, or RPCs, network file system, or NFS, and AppleTalk Zone Information Protocol, or ZIP. This allows two application processes on different machines to establish, use, and terminate a connection, and that is called a session. This performs functions that allows those processes to communicate over the network, performing actions, providing security, name recognition, logging, and so forth. A well-known example from the Microsoft world is NetBIOS, or Network Basic Input-Output System, and lastly, Point-to-Point Tunneling Protocol, or PPTP. So various protocols at this layer ensure that requests and responses between applications can work properly over a session between those end-user application processes. So those were the top three layers of the OSI model. We had the application layer, presentation layer, and session layer, which were the primary focus of developers or system administrators. Now let's concentrate on transport layer, network layer, data link layer, and physical layer, which are the realm of the network engineer. Layer 4, or the transport layer, ensures end-to-end communications, reliability, and flow control. This layer performs message segmentation, where it accepts a message from the higher layers, in other words, the session layer above it, splits the message into smaller units if they're not small enough already, and passes the smaller units down to the network layer for sending. The transport layer at the receiver will reassemble the message. This layer also handles transportation issues between hosts and ensures data transport reliability. So as an example, the two main protocols at this layer are TCP, or Transmission Control Protocol, and UDP, or User Datagram Protocol. TCP provides reliability. It establishes, maintains, and terminates virtual circuits between devices. So two end systems will go through the TCP three-way handshake to establish a connection between one another. Packets are sequenced, and if packets go missing, those packets will be retransmitted. Please refer to the TCP and UDP video for much more detail on the processes used by TCP and UDP. UDP in brief does not provide reliability. If packets are dropped, they're lost, and higher layer protocols, for example at the application layer, need to ensure reliability. Flow control may also be implemented at the transport layer. Flow control will manage data transmission between devices to ensure that the transmitting device does not send more data than the receiving device can process. The receiving device can tell the transmitting device to back off or slow down when no message buffers are available. Session multiplexing also takes place at this layer. This allows for the multiplexing of several message streams or sessions into one logical link, and this layer will keep track of which messages belong to which session. UDP, on the other hand, does not give us that kind of reliability and is normally used by applications such as voice over IP, which do not require retransmission of packets. In certain cases, such as voice over IP, retransmitting packets would be irrelevant, and thus those applications use UDP. UDP is more lightweight, has less overhead, does not do sequencing, or provide the other reliability mechanisms that you get in TCP. One of the well-known analogies to differentiate between TCP and UDP is think of TCP as a telephone call. When I phone you, I get an acknowledgement from you that it's you speaking because you say hello and probably mention your name. If I give you a piece of information over the telephone, such as a string of numbers, you may repeat that back to me to ensure that you got the information correctly. So as an example, if I told you that someone's telephone number is 555-1212, you would repeat that back to me. you would say the number is 5551212 to ensure that both of us know that you got the information properly. So that's a similar mechanism to TCP, where every bit of information that is transmitted is acknowledged. So there's an acknowledgement of receipt of information. If the information is not received properly, it's retransmitted. The analogy used for UDP is that it's like the postal service. If I want to give you someone's telephone number, I may write that on a piece of paper, put it in an envelope, and mail it to you. There's no guarantee that that piece of mail will actually reach you. In the same way, there's no reliability in UDP. The network layer, or layer 3, is very important to us as network engineers, as this is where routers reside. This layer is all about data delivery, where routers route data packets from one device to another. HP and other vendors also have what are called layer 3 switches. Layer 3 switches have router capabilities, so they also route packets within a network. Routers or layer 3 devices choose or select the best path to deliver data based on the information provided by routing protocols such as OSPF, or Open Shortest Path First, and RIP, or Routing Information Protocol. They use the logical addressing scheme of IP version 4 to determine the best path. So in IP version 4, we have a network such as 192.168.1.1 with a network mask. The network mask informs devices that the first 3 octets are network, and that's how routing decisions are done. Please refer to the IP addressing video for more detail with regards to network and host portions in an IP address. And in turn, routers or layer 3 switches will determine the best path to route traffic based on criteria associated with networks. So OSPF, as an example, uses bandwidth to determine the best path. RIP uses hop count to determine the best path. And this is based on the logical addressing format used in IP version 4, and by the same token, IP version 6. There's no reliability of data here. IP is not concerned with reliability and would rely on higher layer protocols such as TCP to provide reliability, or when UDP is used, at the application layer, a protocol such as TFTP provides reliability. IP does not provide any reliability or retransmission of packets. The network layer, or layer 3, provides path determination and logical addressing. Layer 2, or the data link layer, provides physical addressing and access to media. It is concerned with how data is formatted from upper layers for transmission over a given network technology and how access to the network is controlled. As an example, on Ethernet, a MAC address is used as an identifier of a device. So on a network interface card, or NIC, a MAC address is burnt in by the manufacturer. MAC addresses are 48 bits in length, and they're broken up into 2 pieces. We have what's called the organizational unit identifier, and then a unique portion for this specific network card. We'll spend some time looking at this later, but as an example, on my PC, using the command ipconfig/all, I'll be able to view the MAC address of my network interface card. So notice on my Ethernet adapter local area connection, I can see the physical address written in hexadecimal as follows. This portion identifies the vendor, or the OUI, organizational unit identifier, and this is a unique value assigned to this network interface card, or NIC. This is a flat hierarchy of addresses. Unlike IP, this consists only of a vendor code and a unique identifier. When installing network cards, you don't need to ensure that network cards of a specific manufacturer are in one subnet, as an example. It's a flat structure of addresses. Unlike IP addresses, which on the other hand are logical addresses assigned by network engineers and configured to be within a subnet. This layer also provides error detection and in certain cases can correct errors that occur at the physical layer. When using Ethernet as an example, the data has to be formatted according to the rules of Ethernet. However, that data may traverse many links, and at another point in your network, it may traverse a WAN link that's using point-to-point protocol or PPP. So the data link layer ensures that the data from higher layers is formatted correctly for transmission across individual physical links, where the physical link characteristics may vary. First layer in the OSI model, or layer 1, is the physical layer. It defines how data is transmitted, so what state represents binary 1s or binary 0s. So media signal and binary transmission are defined at this layer. It defines the electrical, mechanical, procedural, and functional specifications for the physical link or physical layer. This allows for interoperability. To put that in plain English, notice as an example that RJ45 connectors are used on Ethernet and they would connect to the network interface card of a PC. The standards associated with this interface, RJ45, are different to a V35 connection, which is used on a WAN interface. So the physical characteristics of these interfaces and the specifications for activating the connection are different. On Ethernet as an example, at layer 2, Ether 2 might be used, but PPP or HDLC may be used at layer 2 on a WAN interface. The physical characteristics here are very, very different. So things such as the pins, the voltage, the cable specifications, and the devices that are supported may vary. Copper as an example has different physical characteristics and specifications to fiber. Fiber transmits light, copper transmits electrical signals. The physical infrastructure is very different, and that needs to be standardized. A network engineer needs to know that he can connect an HPPC to a switch provided by a different vendor. The specifications are standardized, so a network engineer knows that he can purchase a Cat5 or Cat6 cable with an RJ45 connector from his local network supplier and plug that into an HP machine without worrying about compatibility. The physical specifications are laid out at layer 1 of the OSI model, and thus we have interoperability between different devices from different vendors because they adhere to the standards at the physical layer or layer 1 of the OSI model. Once again, a software engineer working at layer 7 of the OSI model doesn't need to be concerned with the physical characteristics of Ethernet or ATM or V35 cables. He concentrates on the specifications at layer 7, and vendors providing networking equipment adhere to the standards at layer 1 to ensure interoperability between networking devices. The physical layer is often the easiest layer to identify because it's concerned with physical devices and physical cabling. There are many major functions performed by this layer, and they will vary depending on the physical media. So as an example, cable specifications, maximum cable length, electrical specifications, radio specifications including signal strength, the modulation techniques, the line coding, bit synchronization, and many other options. You'd have to refer to the physical specifications of an individual media type, such as Ethernet, to see the details and specifications for that individual media type. We're not going to concentrate on those. If you were planning on becoming a manufacturer, you would have to manufacture your cabling and interfaces according to those specifications to ensure interoperability and standardization. That concludes this first video discussing the OSI model. In this video, we looked at the reasons for the OSI model and the layers of the OSI model. In the second video, we'll continue the discussion by looking at traffic flows between hosts and a demonstration of the OSI model by sniffing traffic using Wireshark. For more information, please go to hp.com/go/expert1.